What'd you do then? Oh no.
It says 10:45. Have a good weekend.
Yeah, and I turned mine down and it's looking nice, so.
You actually not split it section for us.
All right, so we're going to talk about how waves interfere today. Pretty cool.
Oh, yes.
Okay, this is where we get standing waves. And unfortunately, in high school physics, we just vaguely talk about standing waves. But, okay. So we're going to talk about wave interference. Okay, it says two different material objects can never occupy the same space at the same time. So if Stephen and I want to occupy the same space at the same time, it's physically impossible.
Like
Okay? We know who'd win. Okay? Secondly,
The one with hips. True.
hey, you haven't elongated.
I'm just saying. You get injured.
All that matters is
Which one of you guys that?
Did you not know?
All the back surgery done.
Yeah. You have an elongated butt.
you're saying I have hips?
No.
No, we're saying that you get injured too easily and your hips are rarely
Yeah, like I'm shaped like a pear.
All that
Oh, what that? Compare hips.
Okay. Anyways. So the point is anytime you're talking about two physical materials, they can never occupy the same place at the same time. But thankfully, a wave is not a movement of matter. Did I spit on you? What's that far away?
Thankfully, a wave is. We cannot get through a sentence.
Okay. Since a wave is not matter moving, it's not matter itself being moved, but rather the transfer of energy. Waves can occupy the same spot at the same time. What does that even mean? Good question. Okay? So, mechanical waves are not matter, but rather displacements of matter, so waves can occupy the same place at the same time. Okay, so how do they interact then if they can occupy the same spot at the same time? Okay, this idea or overlapping of waves has a name. It's called superposition. Okay, remember superposition principle. Pretty important here. Okay, so when two or more waves travel through a medium at the same time, the resultant wave, that sounds like a resultant vector, doesn't it?
Yeah.
Okay, we're not going to be doing vectors, but it's the same concept. It's the sum of the displacements of the individual waves. Okay? So we really just add the two waves.
So you tell them two waves going the same way, make a big wave.
If they're on the same side of equilibrium, yes. Okay, so what I'm saying is if waves come into contact with each other and they're both above equilibrium, they constructively interfere. What that means is they make it bigger, bigger, they build, you said build on themselves. But if you have one that's above equilibrium and one that's below equilibrium, they actually constructively interfere, and so they subtract each other out.
Oh, that's gonna be so.
Visual. Yeah, I was gonna say I need a visual.
Small wave, big wave. Big wave.
There's your visual.
That's a
Oh, that's so
I love.
I need to pony up some money and get some materials to show this. Okay, so here, would you agree that both of these waves are above equilibrium?
Yes.
Okay, and they're coming towards each other. Okay, since they're above equilibrium, they're both positive, and you add the waves when they interact with each other. So the two waves come into contact, and I know it's like you're trying to see the process. So really what happens is as they come, they build on each other. So essentially when they're completely superimposed, this plus this gives you this.
then they go backwards.
Orange.
Yep, and then they separate back into their original waves. Absolutely.
So like when you flip it at the same time and they go together and then go back?
Yes.
Is energy lost during that, or is it?
I don't want to say there's probably a very, very small amount of energy that's lost.
Waves
But,
are real good at saving energy. Yes, they are.
So they don't just go like.
well, no, because they're not matter moving. It's a disturbance moving.
So it's rotating?
Okay?
Wait, so
Yeah,
when
this
they're
is
going, when they're going in opposite directions, they make a bigger wave?
As long as they're on the same position from the equilibrium.
But isn't it like the opposite vectors? Because like two come in contact.
Well, I didn't use the vector comparison. I didn't use the
No,
vector.
but like, I'm just saying like kind of
I feel like if you put two waves
because
together,
these
they just
make
like
something
die
better.
out.
Yeah, these aren't dependent on,
Bet.
like, there's no, it's not like a vector quantity or direction. The only thing that's important here is the direction you're on the
Oh,
equilibrium.
see, guys, let me put them together.
Okay,
No, it works.
destructive interference.
Oh, that's, okay, that makes sense.
Okay, so here they're on opposite, so this would be like a positive and a negative. So you're adding the opposite if you want to think of it from a vector standpoint. And so what ends up happening is they destructively interfere, and so one subtracts from the other, and you're left with the what the net overall would be. Okay? So theoretically, if you had two waves of equal amplitude but on opposite sides of equilibrium, when they came together, you would see the rope look like it's not moving, like there's no wave at all.
And it pops back down. What?
If they were equal, have you in order to really see it, you need like a specific, like maybe if I got a slinky, you'd be able to see at least a little bit of it. But I've tried using random things and it hasn't been super
What about a rope?
productive. Even a rope. I mean, you can see like a pulse wave, but I can see what I got, but
What about that
See what I got.
extension cord?
Steven, you actually could take that off, right?
That would work.
I'm just.
You feel like you peeled half of it off.
Oh,
earlier,
why would you
and then
ever?
stuck it back on.
Because I
And
got
I
it
actually.
oh, that is so interesting. Hold on.
You do that yourself.
I just found these crystals.
I don't think I've ever seen someone get
Word, Lauren.
It's probably not long enough,
You
but.
make fun of him for now? How you could just.
Steven, stand up.
You're still little.
Yeah.
You just hold it.
Nice.
Oh! It's hard to do. So see, that's why I don't show visuals.
Wait, no, I actually it was like.
Well, so good. So in theory, I actually have a video that will show this better, but I also haven't talked about what happens when a wave hits a fixed boundary.
We should just show the video.
Yeah, probably. I'm gonna show you the video.
What's the most bad?
Oh,
Video
it's a
better.
fixed
Isn't this
one.
smarter every day?
There's a
It's like
smarter
every
video.
second it goes
Yeah.
together and then it goes back.
Sort of. It's not like on it exactly. It's about more like.
It's a lightweight, and it hits.
Okay, so before I can show that video, I need to show you this. Yeah, I'm gonna actually I'm gonna need to get some specific thing that will actually show that a little bit. Okay, so waves reflect too. Okay? And they act differently if they are at a free boundary or if they're at a fixed boundary. So let me explain what I mean by a free boundary. A free boundary is one that it can move up and down on that boundary. A fixed boundary is where it's fixed in one location, and so it cannot slide up or down.
How come the not?
Oh,
stop.
Okay? So, this is what happens to reflection when you have it on a boundary that is not fixed or it's free. The pulse wave comes in, allows this to come up, and it comes back on the same plane. So what I mean by that is it stays on the same side of equilibrium when it gets reflected. If it's a fixed boundary, when it hits that fixed boundary, it inverts when it's reflected. So as you can see, it starts above equilibrium and then goes back below equilibrium. Now the amplitudes are the same, but it gets inverted. What was that? Amplitude is how much away from equilibrium it is.
Oh, so it's, okay.
It's the same level away from equilibrium, it's just inverted on, it's now negative. Okay? Now, I do have, it's really short, but it's kind of, it's a cool visual.
Wait, so it's free because the not
Way above.
Yes. Okay. So this is going to lead us into what standing waves are, and what's going to lead us into sound when we talk about the first, second, third, and fourth harmonic.
Just like you guys.
I like to play a loud
So that I don't get copyright issues, I'm just going to turn this.
No.
If you don't stop right now.
Reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down.
Wait,
If
what?
I send a rhythmic pulse,
Did you see how it hit the fixed
And came
and
back.
came back
It-
underneath?
Oh.
Did you not see that?
You wrote all
Oh, no.
Yes.
Put it in slow. Put it, yeah, do
Well,
it
have you ever
slow.
played
He's holding it fixed. It's not allowing it to go up and
Watch
down
the speed. I do
barely.
it all the
Not
time.
enough.
Why are you
Tell
so
him to
shit
do it.
over this?
Hey, you should.
as I send a single pulse down to this fixed end, you can see that it reflects upside down.
Oh.
If I send a rhythmic pulse, it reflects on itself.
Well, what
This is the
that?
fundamental
Oh.
mode.
That one I
Sending the pulse at
probably
twice
some
the
long
frequency results in the second
Just like
harmonic.
you soidal.
If I triple the frequency,
Oh my
Ah.
word.
third harmonic.
What is that?
Those are standing waves.
Oh.
So that's like a side.
So
That's
it's pretty cool. And again, I need to get whatever that is. It looked like it was more than just a rope. Like it was a little bit of a wire or some sort of.
It's a.
So what is a standing wave? Okay. So what you saw there is he talked about first harmonic, second harmonic, third harmonic. We'll talk about that when we get to chapter 12, which is dealing with sound, but it has to do with standing waves. And what a standing wave is when you have the same frequency, wavelength, and amplitude, or you have like repeated pulses and you have a fixed end. What ends up happening is as you watch that video, it looked like those waves were just standing in the same spot, didn't it? Like they were just going up and down. It didn't even look like they were going back and forth at all, did it? Just looked like they were going up and down. Okay? And that's what happens when you have frequency, wavelength, and amplitude that are all the same traveling in different directions. So when he was pulsating it 3 times, one wave was going down and coming back and hitting the second wave that he was pulsing and the third wave that he was pulsing. What it created was a standing wave that has a certain amount of nodes and antinodes, which I'll explain what those are here in a sec. Okay? And standing waves are actually very, very, very complicated things. In fact, I know very little outside of just the very basic stuff about standing waves. Standing waves are part of the reason why there are some things with the wave-particle duality that have to do with standing waves and how electrons are follow the Heisenberg uncertainty principle has to do with standing waves. But I don't know much more about standing waves than really you guys will after today. Okay, so standing waves have nodes and antinodes. Okay, so it says a node is a point in the standing wave that maintains zero displacement. So what I mean by this is it stays in the same spot the whole time, which I said if you watched that visual, it just looked like it was standing. It wasn't the waves weren't going back and forth, it just looked like it was going up and down. Well, there's a point then that technically doesn't go up or down at all. Okay? And that's what you would call a node. An antinode would be the points where it's just going up and down at its maximum. And let me show you a visual that will help you be able to figure this out. Turn in your books to page, I don't know what page this is, because my pages are different than yours. But the last page is section 4 in chapter 11. Close to 400, I would assume. It's the last page of section 4 in chapter 11.
Oh, yeah.
Okay, so you should see. I want 389. Okay, I actually want 389. So it should look something like this. Is that what I'm seeing? Okay. So, a node is a place where you have no displacement. An antinode is a place where you're at your largest displacement. So if you're looking at page, 389? Okay? The very first wave there, which would be called your first harmonic wave when we get into sound, how many nodes and antinodes does it have? Anybody care to take a guess based on the definition? Autumn?
2 nodes, 1 answer.
Yes.
The place where over
Okay? There's 2 places where it's at 0 displacement, the 2 ends. Everybody see it? That's why it has 2 nodes.
Well, doesn't the one end technically move up and down?
What was that?
Doesn't the one end technically move up and down because he's going like
Now if you're talking about a guitar, when you pluck
yeah,
a
but when the
guitar.
guy was doing it, he was going like
Yeah, in that example. Yes. In that example. But not, you don't have to have somebody creating a vibration on one end. You can have it fixed on both ends and pluck it in the middle or on the side of the, and that's what you're gonna get when you have a guitar. That should be speaking your language.
That's why we learned his overtime part. Creating a node in the middle of the string.
See, I don't know enough about musical stuff to be able to say yes or no from a physics standpoint on that, but. Okay, so, and there's only, I know you're probably thinking, well, isn't there a max displacement on the positive side and a max displacement on the negative side? Well, the answer is yes, but that's still one location. That's why there's only one antinode. Does that make sense? Okay, well, sometimes some people have asked that question. So, all right, the next one then. Who thinks they can tell me how many nodes and antinodes the one underneath it has? Isaiah?
One with 2 bumps.
Yeah, sure, yep.
3 nodes, 2 antinodes.
Is that correct?
Yes.
On the
Yeah.
one, the second one, though.
Yeah.
It seems
What?
like,
The second one down, yes.
it seems like there's always one less
Okay, where are we?
anti.
There is.
Boom.
Yep. Because there are always going to be two fixed locations, or usually 2 fixed locations.
These are antinodes.
Okay? And then you kind of see the trend here. The third one, you've got how many nodes and antinodes?
4 nodes, 3 antinodes.
Yep.
One antinode.
That's what we just. Yeah, some. I don't remember. Or odd. Okay? Now, the thing that you need to remember about standing waves is this. Same frequency, same wavelength, same amplitude that are traveling in opposite directions. So you get this continual interference that just repeats itself. And so like it just looks like it's standing. It's not it doesn't look like it's moving anywhere, just going up and down in the same location.
Isn't it just multiple waves that are just like
Essentially.
So they're not going the same
What do you mean?
way. Like when it says opposite directions, so the ones right next to each other are
So
parallel
yeah,
to
so
each
what's
other?
happening when he first on that visual we watched, when he sent that first pulse, that pulse was going down, right? And he kept repeating it. So as that first one goes down, hits the fixed region and comes back, it's interfering with its second pulse and the third pulse. And so what you have is this continual back and forth movement above and below that interfere perfectly that it looks like it's just going up and down. I don't know if that made sense.
So it sends it above and then it comes back below, so then it makes both.
What?
Okay.
That's it. We're done with chapter 11.
Oh.
Study, cram for Bible. Hurry.
But it's also
Bible
Yeah,
crap.
this-
Change the cram.
I don't know.
That's why I was asking, but you can only see half the time.
I hate the end of this verse so much.
I know, it's so weird.
That's not anything.
That's it,
that was
crayons?
not